In the first module, we studied the foundations, what digital systems are, how they are specified and implemented, the role of CAD tools, number systems, logic gates, digital circuit characterization, and Boolean algebra for simplification. In this second module, we move forward into more advanced applications of digital logic. We will explore how to design combinational circuits, sequential circuits, programmable logic devices, arithmetic circuits, and even a simple computer processor. This module is where theory truly meets practice. You will see how the concepts you learned earlier combine to create practical systems that solve real-world problems. Let's begin with combinational circuit design. Section 1. Combinational circuit design. A combinational circuit is a type of digital circuit in which the outputs depend only on the current inputs. There is no memory involved, no storage of past inputs. The output is determined instantly by the logical combination of input signals. Examples of combinational circuits include adders, multiplexers, decoders, encoders, comparators, and display drivers. Design procedure. The general procedure for designing a combinational circuit is as follows. State the problem clearly, define what the circuit should do. Identify the inputs and outputs. Construct the truth table, list all possible input combinations and their corresponding outputs. Obtain Boolean expressions from the truth table. Simplify the Boolean expressions using algebra or Karnaugh maps. Implement the simplified expressions with logic gates. This systematic approach ensures that the design is correct, efficient, and easy to implement. Multiplexer, MUX. A multiplexer, often called a data selector, is a circuit that selects one input from many and routes it to the output. For example, a 4-to-1 multiplexer has 4 inputs, 2 select lines, and 1 output. The select lines determine which input is connected to the output. Multiplexers are widely used in communication systems, computer memory selection, and data routing. Decoder. A decoder performs the opposite function of a multiplexer. It takes a binary input and activates one of several output lines. For example, a 3-to-8 decoder takes a 3-bit input and activates exactly one of 8 output lines. Decoders are used in memory addressing, instruction decoding in CPUs, and display systems. Encoder. An encoder is the opposite of a decoder. It takes multiple input lines and converts them into a binary code. For instance, a decimal to binary encoder takes a 10-line input, 4 digits 0 to 9, and converts it into a 4-bit binary output. Encoders are used in keyboards, data compression, and priority selection systems. Comparator. A comparator is a circuit that compares two binary numbers and indicates whether one is greater than, less than, or equal to the other. Comparators are vital in arithmetic circuits, digital measurement systems, and processors. 7-segment display. A 7-segment display is a device used to display decimal digits using 7 LED segments. To drive a 7-segment display, a digital circuit converts binary inputs into the appropriate signals to light up the correct segments. This is commonly seen in calculators, digital clocks, and counters. Parity generator and checker. A parity generator adds an extra bit to data for error detection. For example, in even parity, the extra bit is chosen so that the total number of ones is even. A parity checker verifies this at the receiving end. Parity circuits are essential in digital communication and data storage systems. Designing larger circuits. One of the strengths of combinational design is that larger systems can be built by combining smaller building blocks. For example, a multiplexer can be used inside a larger memory system, and a comparator can be used in a sorting circuit. This modular approach mirrors how engineers tackle real-world problems. Section 2. Sequential circuit design. While combinational circuits are powerful, they are limited because they lack memory. In real life, we need circuits that can store information, remember past inputs, and change behavior over time. This brings us to sequential circuits. A sequential circuit is one where the outputs depend not only on the current inputs but also on the history of inputs. This is achieved by including memory elements. Flip-flops. The most basic memory elements are flip-flops. A flip-flop stores one bit of data and has two stable states, 0 and 1. Types of flip-flops include SR, set reset, flip-flop, the simplest type, with inputs that set or reset the stored value. D, data, flip-flop, stores the value of the input when triggered by a clock pulse. T, toggle, flip-flop, changes state each time it receives a clock pulse. JK flip-flop, a versatile flip-flop that can act as SR, D, or T depending on input conditions. Flip-flops are the foundation of registers, counters, and state machines. Flip-flop applications. Flip-flops are used in data storage registers, frequency division, counters, synchronizers in communication systems, clock generation. Sequential circuits rely on a clock signal, which is a periodic square wave that coordinates operations. The clock determines when flip-flops change state and ensures synchronization across the system. Counters. A counter is a sequential circuit that goes through a predefined sequence of states. Binary counters count in binary numbers. Decade counters count from 0 to 9. Up-down counters can count in both directions. Counters are used in timers, digital clocks, frequency measurement, and event counting. Registers. Registers are groups of flip-flops used to store multi-bit values. A 4-bit register, for example, can store any 4-bit binary number. Registers are used in CPUs to hold data, instructions, and addresses. State machines. A state machine is a sequential circuit that moves through a set of predefined states depending on inputs and the clock. State machines are powerful tools for controlling complex digital systems such as vending machines, traffic light controllers, and CPUs. Section 3. Programmable logic devices. As digital systems grew more complex, designers needed more flexible building blocks. This led to programmable logic devices, PLDs. These are circuits that can be programmed to implement a wide range of logic functions. Read-only memory, ROM. ROM is a type of memory where data is permanently stored during manufacturing or programming. It can be used as a programmable logic device because any truth table can be implemented by storing the appropriate outputs in memory. For example, a ROM can be programmed to act as a decoder, encoder, or even a small arithmetic unit. Programmable logic array, PLA. A PLA is a programmable device that allows the user to configure both an array and the OR array. This makes it highly flexible and capable of implementing complex combinational logic functions. Programmable array logic, PAL. A PAL is similar to a PLA but with a fixed OR array and programmable an array. PALs are easier to design and faster but slightly less flexible than PLAs. PLDs have paved the way for more advanced devices such as field programmable gate arrays, FPGAs, which are widely used in modern electronics for prototyping and even final products. Section 4. Digital computing systems. Now we come to the grand application of all digital design principles, the digital computer. A digital computer is essentially a system built from combinational and sequential circuits that performs arithmetic, stores information, and executes instructions. Arithmetic circuits. The most fundamental arithmetic operation is addition. A half adder adds 2 bits and produces a sum and a carry. A full adder adds 3 bits, including carry in, and produces a sum and carry out. By chaining full adders together, we can build adders for larger binary numbers. Multipliers are more complex, but they are built using repeated addition and shifting. Modern processors use optimized multiplier circuits for efficiency. Memory design. Memory is essential for storing data and instructions. Two common types are ROM, read-only memory, non-volatile memory that retains data permanently. RAM, random access memory, volatile memory that stores temporary data. Memory is organized into words of fixed length, and each word has a unique address for quick access. Design of a simple CPU. Finally, let us consider the design of a simple central processing unit, CPU. A CPU typically consists of arithmetic logic unit, ALU performs arithmetic and logical operations. Control unit, directs the flow of data and instructions. Registers, store temporary data and instructions. Memory interface, connects the CPU to external RAM and ROM. The CPU operates in cycles, fetch an instruction from memory, decode it, execute it, and then fetch the next instruction. This fetch, decode, execute cycle is the heartbeat of all digital computers. Section 5, Closing Summary. We have now completed Module 2 and with it, our journey through logic and digital systems. Let us recap what we covered in this module. We began with combinational circuits, including multiplexers, decoders, encoders, comparators, display systems, and parity checkers. We moved to sequential circuits, exploring flip-flops, counters, registers, clocks, and state machines. We studied programmable logic devices, including ROM, PLA, and PAL. We then applied all these concepts to digital computing, including arithmetic circuits, memory, and the design of a simple CPU. This module shows how the basic building blocks introduced in Module 1 combine into powerful systems capable of computation and control. Final course wrap-up. Across both modules, we have traveled from the most basic concept of binary digits all the way to the design of a simple computer. Along the way, you have learned about number systems, logic gates, circuit characterization, Boolean algebra, combinational and sequential circuits, programmable devices, and digital computing. Digital systems are the foundation of modern technology. Every smartphone, laptop, medical scanner, industrial robot, and satellite is powered by the principles you have studied in this course. As you continue your journey in engineering, computer science, or electronics, remember that mastery of logic and digital design will open the door to understanding and creating the technologies that shape our world. Thank you for your attention, and congratulations on completing this course on logic and digital systems.